Hello to this video. In this video, I would like to talk to you about Maxwell's equations. Maxwell's equations are the unified theory of all the electromagnetic effects we have been looking at. And I will, in this video, introduce Maxwell's equations, first of all, show you the equations, and then we will talk about the first Maxwell equation in more detail. So let's get started and look at Maxwell's equations. So these, they are in all their beauty. You can see all of the 4 Maxwell equations. So what Maxwell did in the years 1861 to 1864, he took the experimental findings and put them into one unified theory. And we will first of all check out this first equation, and before starting, I would like to introduce to you the different variables that you see in these equations. So on this slide now you can see the different variables that we will use, starting out with the electric magnetic field vector, the displacement field vector, and the current density vector. So these are the 3 electric property vectors. Vector always means that we have a direction, so a vector points into a certain direction, a field points into a certain direction, and we have an amplitude. And the vectors are notified by giving here the vector sign above the corresponding quantities. The units are given here on the right side. The unit equations I always give with these square brackets here. So the square brackets mean that we have a unit, and for example, the magnetic field vector has a unit of volt per meter. The current density vector has a unit of ampere per square meter. We are using SI international units in all of the lectures here. So coming to the magnetic field quantities, we have the magnetic field vector and the magnetic flux density vector given here as H and B. Also both these are vectors. That is, also the magnetic field has a direction and it has a magnitude. So also here we need vectors to describe the magnetic field effects. The 2 magnetic field vectors are actually related by the material properties, as we will see in the next video. Sometimes you find that all of the theory is given in terms of B, and also B is called then the magnetic field vector. Sometimes, as I did it here, B is the magnetic flux density vector, and then H is the magnetic field vector. Important is the fact that the 2 are related by the material properties, that is by the permeability. So we can calculate one from the other, and of course in the equations we can, instead of writing this in terms of H, we could also write this in terms of B if we put the permeability in additionally here. So it can, the form with given with H as here and B in the second equation can also be converted into a form where we only have B, for example. And this is a bit historic of what is H and what is B and what the names exactly are. But in the end, it's important that you take a valid form of the equations with the correct permeabilities added in, and then the results will be correct, because so far the Maxwell's equations have been shown to very well represent experimental results that we are observing. Okay, then we also have the charge Q in the Maxwell's equations, and finally we can also derive the electric current and the magnetic flux from these quantities. So the electric current means that we take the integral over the electric current density. So we integrate the density vector here in order to get the electric current. And the magnetic flux corresponds to the electric current in a sense that we integrate the magnetic flux density in order to get the magnetic flux. That's why I kind of like the term magnetic flux density, because the surface integral then gives you the magnetic flux. Okay, so let's first of all now look at the first Maxwell equation and where it's coming from. So experiments by Ampère had shown that Ampere's circuital law is valid. That is, if we have a current I that is going upwards, then we will have a magnetic field around this conductor. And that has been observed by Ampère, and it has been summarized in this equation where the electric field, where the electric current can either be just the current I, as in this case, so then this integral would just be the current, or we can also look at the magnetic fields that are generated inside a conductor. If you want to do that, we have to look at the current density that is going through the surface that is enclosed by the contour we are using to integrate the magnetic field. So this C of A here means, and the circle in the integral means that we take a closed contour somewhere in space, and this closed contour surrounds an area A, and then we need to integrate the current density over this area A in order to obtain the total contribution of this electric flux to the Ampere's circuital law. Okay, so this is what we already looked at in the previous video. We have a current I, we have a magnetic field H. All nice so far. What Maxwell then started considering is this case that we have not just conductors, but we also have a capacitor in here. A capacitor is a device where we have in the middle here a dielectric medium. That is, we don't have any conduction current in this area. We don't have any charges that are physically moving through this area here. And so if we just look at this equation, it would mean, okay, if we are charging this capacitor here, so charges are flowing onto the capacitor. For example, charges are flowing onto here, and they are flowing, positive charges are going upwards on the other plate. Then that would mean that we have around the conductors, due to the charging, a magnetic field. And also on the other side here would have a magnetic field around the conductor that corresponds to the right-hand rule. In the middle of the capacitor, as we don't have any conduction current here, there would be no magnetic field, because from this equation up here, Ampere's circuital law, we only have a magnetic field whenever we have charges moving, and there are no charges moving here in the middle, in the sense that we do not have a conduction current here. And this, Maxwell thought, is a bit strange. So how can it be that we have a magnetic field here, then the magnetic field stops, and then it continues here, and we again have a magnetic field here? So what he proposed is that something else must be happening here, and this is what is that he proposed there must be a magnetic field in here, and he linked this magnetic field to the displacement current. Now, a displacement current is an electric effect where you have, if you put some conductor in here, you will see that this conductor will also have charges on the upper and on the lower side that are obtained by the electric field. So charges will also be displaced in a conductor that is placed in the center of this capacitor here. So even though no charges can flow through the dielectric medium, the field penetrates the dielectric medium, and this penetration of the dielectric medium with the electric field means that if we put a conductor in, we still get a charge separation that is observed on the conductor in the middle here. And this is what is called a displacement current, that we don't have charges moving, but if we have changes in the electric field, we get still a displacement of charges somewhere in the center of such a dielectric medium, or also to the top or to the bottom. So anywhere in the dielectric medium, we will get charges displaced. Actually, if this is not vacuum, but if it's a material, then of course also, even if the charges cannot move so cannot leave the atoms, cannot move from one side to the other, we can get a change of the charge distribution within each atom, so that we see or each molecule, so that we see, depending on what kind of material we have, that the negative charges are moving upwards, for example, and the positive charges are at a lower position compared to that. So we get a displacement of the charges, even though we have no conduction current. And this is what Maxwell proposed then, that this displacement current also must cause a magnetic field. And to include this in Ampere's circuital law, he added this term down here, so that the change in displacement or the displacement density, D is the displacement density, the change in displacement density over time also causes a magnetic field. So only while this capacitor here is charging or discharging, so that charges are flowing onto the plates or from the plates, will we have this effect, and we will have a magnetic field around the dielectric as well. I mean, also only while the plates are charging will we have a current in these wires. So if the plates are not being charged, this is all static, because if there's no charging effect going on, the capacitor blocks the current, so we won't have any current. So if the capacitor is not charging or discharging, there will be no current in the wires and no current in between here. So in the static case, there's just no magnetic field because there's no current flow. But in the case where we are charging the capacitor or discharging the capacitor, we also have a change of the electric displacement, and this causes a magnetic field inside the capacitor here. And this combined equation now, so Ampere's circuital law combined with this addition here by Maxwell, that is what is called the Ampère-Maxwell law. So the Ampère-Maxwell law is this full first Maxwell equation. So this is again the first equation that Maxwell put down. Here you can see again the unified theory. So this is what we now talked about. The Ampère-Maxwell law is Ampere's circuital law, which has additionally this term here added in by Maxwell, taking care of the displacement currents in dielectrics. Okay, thanks for watching. Next video we will continue with the second Maxwell equation.